This is 6.4, graphs of the sine and cosine function. This red graph that you're looking at is right down here at the bottom left, f of x equals sine x. This is actually the parent function for all sine curves. You can manipulate them and transform them just like any other quadratic function or linear function or exponential function. I can move it up and down, I can stretch it out, I can make it narrower. I can have more waves within a smaller period of time. So we're going to take a look at all those different kinds of transformations that go along with these graphs. And more specifically in this section, we're just going to take a look at two different ideas, one of them being called amplitude and the other being called midline. And you may have heard of amplitude before in physics or in another science class. Amplitude happens to be a very simple idea that describes the distance from the midline. Well, so we can't do anything with amplitude unless we know what midline is. So what is midline? It is going to be a line that runs down the middle. Okay, so I'm going to go ahead and in blue, I'm going to outline where the midline should be. So it should cut this graph in half, but it's a horizontal line. So I'm going to just do this with dashes, but this is where the midline would be. It's going to cut that graph right in half, so it's going to be almost like if I folded it over hot dog way, it would be the same distance from the top of the graph to the bottom of the graph. And that is going to be our amplitude. So in purple, it says that it's the distance from the midline, the amplitude is. So that means, well, distance from what? Midline to where? Well, it's the distance from the midline to the highest or lowest point. So oh, that doesn't show up very well. Let's try orange. There we go. So if I were to measure the distance from that highest point to this midline, it would have a length of 1 unit. And therefore my amplitude would be 1. Also, same thing over here. This is my lowest point, and it also has the same exact distance from the midline. And that should always be true. Now, just because this part of the graph is underneath and it's at -1, this point is at -1, it does not mean that the amplitude is negative. There's never, ever such thing as a negative distance, or at least that we know of yet. So don't say that your amplitude is negative. In this case, I would say that my amplitude is 1 unit, and my midline, and because it's a line, we're going to put y equals here. And that is wherever that blue dot is going across the y-axis. So on the y-axis, that blue dot is going through 0, so y equals 0 is the midline. So let's take a look at the parent function for cosine. Okay, so this is the parent function for cosine. It looks just a little bit different than the sine curve. So let's take a look at the midline for this function, and I'm going to do this in blue again. So if I were to cut this function horizontally in half, it would be on this line yet again. So down here, I'm going to tell you that the midline is y equals 0 again. So let's see if we can determine the amplitude. So I'm going to find the highest point, or one of them, on this function, and it looks like one of them is right here. And the distance from that point to the midline happens to be 1 unit. And now I'm going to find the lowest point as well, and it should be the same if I've done this correctly, and indeed it is. It is 1 unit, and therefore the amplitude is 1 unit. Now, sometimes you don't want to have to worry about looking at a graph. You want to know what the amplitude and midline are immediately, so let's take a look at how to determine that. Okay. So the first function that is written here is y equals sine x. And this is our parent function, which, if you recall, had an amplitude of 1 and a midline of 0. we can actually see these numbers within this function. Can't see them right away because they're hidden, but they do exist. In front of the sine function here, that is where that 1 lies, and it's being multiplied by that sine. So the coefficient of sine is going to represent our amplitude. So where is the 0 part? Well, if out to the side, if I write plus 0, that now matches my midline. So these are rules that we're going to follow to determine our amplitude and midline for the rest of these functions. So the coefficient of your trig function, either sine or cosine, is going to tell you your amplitude. And at the very end, if you're adding something to it, that's moving your function up or down, and that's going to be your midline. So let's take a look at this next problem. I'm going to do this one in blue. And let's choose a couple different numbers. Let's make this 2 sine x. So in this case, let's try to determine the amplitude and the midline. So the amplitude is going to be the coefficient of sine, which in this case is 2. So that's all I need to know. So the amplitude is 2. Now midline, I still don't have anything being added out to the side here. So my midline is still y equals 0. And speaking of, I forgot to put the y equals before. So there we go. All right. Let's take a look at another one. How about y equals, I'm going to put cosine in here this time, and it shouldn't matter. It's going to have the same rules as sine. We can do 1/2 cosine x plus 5. So let's try to determine our amplitude and our midline. I'm going to do the y equals right now so I don't forget. So the amplitude, once again, is the coefficient of my trig function, which is 1/2. So 1/2. And my midline is going to be the guy that's all the way out to the end, either added or subtracted. If it's added, then it means that my midline is positive. If this is subtraction, then it means that it's negative. So this would be positive. And let's do one more. So y equals, we'll stick with cosine this time. And I'll do this one in orange. So how about -7 and then -2. Now this we want to be kind of careful with because the amplitude, remember, can never be negative. There's no such thing as a negative distance. So this right here just tells me that it may be flipped upside down, but the amplitude is still a positive number. The distance from the midline to the highest or lowest point is 7 units. So it's kind of like an absolute value. So I'll write that below it. It's the absolute value of the amplitude. And then the midline, since I'm subtracting 2 here, just means that this is going to be negative. Okay, so the next part of this tutorial, we are going to try to determine how to find exact values. And we need to make sure that we know exactly what exact values are. Exact values can contain radicals, like square root symbols, and they can be fractions, but they cannot be decimals. So no decimals anywhere, okay? So I want you to look at the problem I have written down here. I'm going to try to find out what the sine of 30 degrees is. Now, if you remember, just by looking at that cardboard stock that I gave you with the unit circle on the front, on the back, there are some very specific values that are very popular, and this is one of them. Now, in the unit circle, which I have drawn to the right, if I draw a 30-degree angle here, this is my theta, 30 degrees, okay, then this point has some y value, so this would be the x value, and this would be the y value, because we're dealing with sine. And I want to know what it is. And some of these have really nice exact values, and they're really useful. And from your previous classes, you should remember, or at least try to remember, your special right triangles. And watch what I do here in this picture, and I'll show you where the special right triangles come into play. I'm going to make a right triangle here. Okay? And I'm going to blow that triangle up right over here so I can draw it a little bit easier. So there we go. This is the 30-degree angle. If this is 90 degrees, then that makes this angle up here 60. So this is a 30, 60, 90 triangle. And if you remember correctly, if the shorter side is x, then the hypotenuse is twice as big, and the side opposite the 60-degree angle is the smaller side multiplied by the square root of 3. Now, if we were to do this but without x's, like let's say that x is equal to 1, then that means that this side here is a 1, and the 2x side is just 2, and the other side, x times the square root of 3, is just the square root of 3. All right, there we go, nice and clean. Now, if you remember also from way back when, your SOHCAHTOA rules, sine happens to be opposite over hypotenuse. So I'm going to write that out. So the sine of my degree measure is opposite over hypotenuse. Now in this particular case, this is the sine of 30 degrees, which happens to be right here. Okay? So the side opposite the 30-degree angle would be this side over here, which is 1. So I'm going to write that down. So the sine of 30 degrees is equal to 1 over the hypotenuse of this, which would be 2. So, does this look like an exact value? Well, sure it does. There's no decimals. It's a very nice fraction, actually. And this has the equivalent value of 0.5, but we're not going to write 0.5 because there's no decimals allowed in exact values. So, using this same exact triangle, what would the cosine value of 30 degrees be? So I'm going to write this right below in blue, cosine of 30 degrees. Now, the cosine of 30 degrees, if you remember, it was adjacent over hypotenuse. So adjacent over hypotenuse. And adjacent is always kind of like the odd side, the side that doesn't look like the opposite nor the hypotenuse. So in that case, that would be the square root of 3. So I'm going to put that in the numerator as my adjacent side. The hypotenuse is still 2. So square root of 3 over 2. And this does look like an exact value because there's no decimals and there are a radical and it's simplified, so we are good. So that's one way that you can do this. And you can do this with 60 degrees or 90 degrees because those are all the degree measures in here. And there's one other degree measure that's very useful that also has to do with exact values. So see if you can remember what kind of a triangle that was before I draw it. All right. If you said 45, 45, 90, you would be correct. So I'm going to blow this green triangle up so we can see it a whole lot better. So this is my right angle here, 45 degrees and 45 degrees. And the relationship with this, if x was equal to 1, then both of the legs would be congruent, and the hypotenuse would be the square root of 2. So down below, let's see if we can determine the sine and cosine values of 45 degrees. Oh, come on. Blue is not working. There we go. All right. So in order to do the sine, that means opposite over hypotenuse. And it doesn't matter which 45-degree angle that you choose because they're both the same. So I guess I will choose this one. So the opposite side here would be 1. And the hypotenuse is the square root of 2. Now, the problem with this is we typically don't leave radicals in the denominator. Even if you see that happen in other places, it's technically not the best way to write it in mathematics. So we're going to do what's called rationalizing the denominator, and it has a very simple process. All we're going to do is we're going to take this fraction, and we are going to multiply it by the square root that we want to get rid of, which in this case is the square root of 2. So numerator and denominator. So by multiplying fractions, we're going to do the numerators together. So 1 times the square root of 2 is the square root of 2. And the square root of 2 times itself is just going to be 2. So that is what I am looking for. And that is my exact value for the sine of 45 degrees. So if we did the cosine of 45 degrees, well, that's the adjacent side. So if this one was the opposite side, then this one would be the adjacent side. And if you can see this, I'm still going to get 1 over the square root of 2, which I already determined to be the square root of 2 over 2. And that's very interesting that both of those trig functions have the same exact x and y value as each other. But if you think about it, if you look at this picture, this point in red is exactly halfway between 0 and 90 degrees. So it would kind of make sense that they would have the same exact coordinates. So that's how we determine exact values.